Welcome to this course, and in today's talk, we are basically going to describe how this public key crypto system is important in our day-to-day life and how we use it. For example, when we use it in case of end-to-end encryption, how these concepts are useful, or sometimes while SSL or SSH case, we also use this concept of public key crypto system. So the basic idea is what is public key crypto system and how this public key crypto system is being built and what could be a kind of basic history for this. So that is the basic idea for today's lecture. So as usual, as you understand that in case of cryptography, the basic idea is that a sender is there who is trying to send some message to some recipient. So here in this particular case, here the boy is the sender and the recipient is this girl. Okay, but the problem is the boy wants to send this message to this girl through internet. Up to this, there is no problem. But the problem is a bad guy is there to listen what is being sent. That means if the boy wants to send some message to the girl, then certainly this bad guy will able to see what is being sent. So as a result, the boy will certainly not be going to send the original message. In cryptographic term, we call this original message as plain text. So he will not certainly send the plain text to the girl directly because there is a bad guy who is always trying to listen. So in cryptographic sense, when we call only listening, we call a terminology, we'll use a terminology which is known as eavesdropping. That means only listening, nothing else. But it may happen that the adversary may be little more powerful in which he can not only listen the message but he can modify the message. In that case, it could be considered to be more vulnerable or more harmful character as an adversary. So we will talk in details about all those kind of adversarial activities, but for the time being, let us assume that this bad guy is always trying to eavesdrop. That means he is eager to listen what is being sent. As a result, this boy will certainly not send the plain text, but what he is going to do, he is going to use some kind of lock and key business. That means he is going to lock the plain text by using some key. So in mathematical sense, by using some mathematical tools, he is going to convert the plain text into a random looking ciphertext, and then he will send this ciphertext, that means the locked message, through this internet channel to this girl. And this process is known as encryption. That means by using some mathematical tools, converting the plain text into ciphertext is known as encryption. So after encryption, the boy will certainly send the locked message, that is ciphertext, through this insecure channel to the girl. And when the girl will receive this message, the girl will certainly wants to get back the plain text. What she is going to do, she is again going to use some key, that means a mathematical tool, through which she will able to convert the ciphertext into plain text, and this process is known as decryption. So we had already learned about all those things in my first video. So encryption, decryption, plain text, ciphertext, eavesdropping, etc. So here two keys playing the most important role. Okay, these two keys. If by any means this bad guy will have this key or this key, then he will have certainly some extra advantage in getting the information. So the question is how this key could be useful. And in this talk, I will show you, first I will put forward an important question, then I will show you a kind of real life scenario how that can be overcome, and then I will come to the basic idea of public key crypto system. Okay, so now it may happen what I have already explained in case of Caesarian cipher. If you remember in my first video, I have already explained, or maybe in the second video, I have already explained what is Caesarian cipher. Is nothing but a SIP cipher. But the important point here we must note is that the Caesar and his subordinate, they must carry the same key. That means before going to the war front, Julius Caesar and his subordinate must know about the key. So both Julius Caesar and his subordinate must agree upon the common key. Okay, so that is why this kind of crypto system is known as private key crypto system or secret key crypto system, because this information must be known to both of them but at the same time not to the adversary. Okay, so it's very important, and in practical scenario, in most of the cases, even today, we also use the symmetric crypto system. Okay, but if we look at the problem in a more detailed way, suppose this boy wants to send the message to this girl, but the problem is the boy and the girl, they stay, say, opposite half of the world. That means far away. So the question is, even it may happen that the boy may not know the girl or the girl may not know the boy, and they want to exchange some message. So under the situation, the question is how they will agree upon a common key. So that's a very interesting question. And if this question was actually asked around late 1980s around. So before 1976, it was like considered to be an unsolved problem, and people might have thought about it, but they couldn't get any solution of it. So now you can understand, if they are staying far apart, so they, if they are staying far apart, then how come they will be able to communicate with some uh, encryption and decryption process by using some key. So in case of symmetric key, both the keys has to be the same, and in that case, both of them, they should privately send this key. Now, if they don't have any means through which they can send, in case if the adversary is present, then the question is how they are going to agree upon a common key. So that was a very nice question. Okay, I think the question is clear to all of you. Do you have any doubt regarding the question? The question is how they will agree upon a common key, because they are far apart. They even may not know each other. It may happen. Then how they are going to communicate with each other by using some keys which are common to on both sides. Okay, that's the basic idea. Okay, to understand this, let us have a very toy example, and I will give you a kind of hints how to do that. Okay. So suppose a kind of scenario in an examination scenario. So suppose there is some university, and in that university some controller of examination is there. Okay, who is actually taking in charge of all the activities regarding examination. And he is a very strict guy, and he follows almost all the rules, and he is very serious about the security of the question papers. Okay, so the university has a kind of agreement that the question paper will be set by some external experts. That means the external expert will prepare the question paper for the students, and then that question paper will certainly appear in the examination hall. Okay, if that could be the scenario, then the question is how the question paper, which is being made by the external paper setter, will reach to the controller of examination securely. So that's the very big headache for the controller of examination. Okay, the idea is, the best thing could be if the paper setter will come personally and hand it over to the controller of examination, then that could be the best possible solution. But most of the cases, as you understand, the external paper setters, they stay a little far off, or they may not agree upon that they will come personally to hand it over. So what they need, they require a third person. That means a postman. So that is still now, that is the scenario that, okay, the controller of examination will certainly receive the question papers from the external of examiner. So that means the postman will help the controller of examination in collecting the question paper from the external paper setter. Okay, so that is the scenario. But the controller of examination is very strict, and he is very serious about the security of the question papers. As a result, he wants to have a kind of simple solution for that, so that he will be very happy to receive a secured communication through the postman, so that the question paper should reach the controller of examination very securely. So can you think of any idea under this situation, how, what should be kind of mechanism? Now please try to come up with your own solution, and let me know. Okay, please, anybody, any idea that how this could be done? Is the question clear to all of you? Is the situation clear? So how this could be done? Any idea? Anybody may come up with any solution. Okay, so if not, then we can come up with a solution here. Okay. So suppose it's a protocol maintained by the controller of examination. Suppose the controller of examination had this infrastructure like a box to collect for collecting this question paper and a lock and a key. You can understand this is a lock and key by like the tap lock and key. That means you can tap it to lock it, but you cannot open unless you use this key. Okay, so for locking the key, I mean locking the lock, you do not require the key, but to unlock it, you need a key. Okay, so he is going to use two sets of not same thing. Okay, they are not just the copy of the same thing, but two different sets of lock and key and a box. Okay, mind that uh, for security reason, the controller of examination has strictly maintained this protocol like his office will not have any extra copy of this key. That means this lock and key is a single copy and this lock and key is a different but is a single copy. That means you cannot have two copies of the same key. Okay, so that he has followed. Now what he will do, he will send this box, the key and the lock through this postman to the paper setter. Okay, so now the postman will carry all those things and he will take it up to the controller, up to the external examiner. Now when the question paper will be ready, the paper setter will put the question paper inside the box, and as he has the lock and key given by the controller of examination, he will put the lock and key and keep the key with him and give the locked box to the postman. So you can understand that he is not that fool to give the lock and key both to the postman. He will suddenly keep the key with him and give the locked box to the postman. Now what the postman will do? The postman will carry it and reach it to the controller of examination. Now if I ask you the question, how the controller of examination will open this? Any clue that you can give me? How the controller of examination is going to open this lock? Any idea?
COE will lock the box with the another lock and key and send it back to the external paper setter.
Okay, so that's one of the idea. Any other idea? Any other idea that you can think of? Okay, he has given a smart idea. So what he says, okay, now why there are two copies of things? Now what he will do a lock, he will do a lock and key by using another set of lock and key. Okay, now the box is locked by two different locks. Okay, instead of opening it, he is giving extra lock on it, and now through this postman he sends the locked, which are locked by two locks, to the paper setter. Now what paper setter will do? Now paper setter has his own lock and key now. So by using this key, he unlocks the lock that he locked initially and sends it back to the controller of examination. Now you can understand that the controller of examination has his own key to open this lock, so he can unlock it and will certainly get the question paper, and he would be very happy to do so, because through this protocol the postman will not be able to get the question paper according to his knowledge. Is the protocol clear to all of you? Any question till now? So you can see that it's a very smart protocol. It may cause like two times the box may go and back, but it's still a very good protocol, so that he may think that uh, it won't be possible for the postman to open this box. Okay, so the postman, I mean this controller of examination may think that this postman, I mean he is a very smart guy and he is capable of getting the question paper in a very secure way. But cryptography is not like that. So here anything may happen. Now let us have a look at another scenario where this postman may be a notorious one. Okay, so if you remember, we had the similar protocol. So initially the controller of examination will give a box as well as two lock and keys, and the postman will carry this lock and keys up to the external of examination. Now a twist in a story, so it's very interesting. Now when he will receive a box and a lock and a key, what he is going to do, he is going to produce another set of lock and key on his own, maybe of similar looking. Okay, and then he will carry, note that he will carry his own lock and key and the box to the external of examination, keeping the lock and key that was actually produced or given by this controller of examination. Okay, now it's a point that what he will understand that okay, postman carries this log box and key from the controller of examination. So when the question papers are ready, he just put inside the box and keeps the lock with him, keeps the key with him, and send the locked box through this postman to this to him. Okay, now what the postman will do? Any idea what the postman will do? Any guess?
He has a duplicate key.
So he has a key on the lock with him. He will just lock it and give it.
Yes. So he has his own key, but he doesn't have the duplicate key. Note that he does not have the duplicate key.
He has the controller of the examination's lock and key.
Yes, but he won't be able to open this because this lock and key is not a duplicate. Because you won't be able to make a duplicate copy of this. That was ensured by the controller of examination. This lock and key say maybe a special type that for him it would be not be possible to make a copy, but he made his own lock and key, similar looking but a different lock and key. So he now does not have the key with him because the key is with him. Then what he is going to do? Any idea? Think what he is going to do then. So think you as the postman and you are very smart. What you are going to do then?
So then I will lock the box with another lock and key, then send it to the external paper setter. And
Yes,
he
very good.
thought
So
that
see,
controller of examination send
very
the
good.
box.
Yes. So what now he is going to do? He will use the now the lock and key given by the controller of examination. Okay. So what he will do? He will use a lock and key here and sends it back to him. Okay. Now what the external paper setter will understand? External paper setter will understand that okay, according to the protocol, this lock has come from the controller of examination. So he will unlock it by using his own lock and key and sends it back to him. Now note that this key is with the attacker. Now because this lock and key was initially given by the controller of examination, So now he can unlock this to see the question paper. Now you can understand that he can see the question paper, he can modify the question paper, he can sell the question paper, whatever he wants he can do, and then he can again put the question paper in and sends it to the controller of examination. Now what the controller of examination will think? The controller of examination will think that this box, this lock was actually given by him, and this must be coming from the external paper setter. According to the protocol, what he is going to do? He is going to put the extra lock on it and sends it back to the postman. Now, what the postman will do then? The postman will unlock it by using his own lock and key and sends it back to the controller of examination. Now, the controller of examination is very happy to receive this locked box, and he has his own key, and by using his own key, he can open it and he can check the question paper. Now, you can understand that whatever question paper that he is going to receive is a compromised one, because this guy might have modified it or he has already seen the question paper. Okay, so it's a nice way of seeing the thing. That means that's cryptography, and this kind of things are known as man in middle attack. So I'm giving you a good homework. It could be a pleasant homework. So many of you might have already seen this movie MI4, the Ghost Protocol, so Tom Cruise movie. So there you might have seen one scene in a Khalifa, Burj Khalifa scene, where the similar kind of attack was mounted. So it is a good and pleasant homework for you to tell me in my next class that what was actually the portion where this kind of attack was made, and this attack is known as man in middle attack. So man in middle attack, and you will be surprised to know that this kind of attack is very strong and powerful attack, so that this kind of attack could be mounted in real life on internet by when you are going to use any kind of public key crypto system. Is the attack clear to all of you? Any doubt or any question till now? Clear, hopefully. Okay, so let us again then come to our digital world. So till now we were in our physical world. Now again come back to our digital world, where we had the similar kind of question, that the sender and the recipient was there, and bad guy is trying to always listen what is being sent. So till now I have assumed that he is just listening, not doing anything malicious, which is active adversary. That means he is not doing anything actively. So he is just only listening the packets. Like that means in internet you can think of when the packets are being sent, he is just only listening the packets, or he is only seeing the packets and not modifying or not stopping the conversation between them. Okay. As I just now mentioned, if they are staying far apart, so maybe the opposite hub of the globe, then the question is how to uh, decide upon a common key. The problem that just now we discussed about. That means if both the keys are same, then we can use the symmetric cryptography. But as you understand that having the same key, if they're far apart, then that could be really a challenging job. And that kind of questions were really asked till 1976. And it was in 1976 when Diffie and Hellman, they for the first time, so this is Hellman and this is Diffie, so they for the first time, it's 1976, came up with a nice path-breaking paper, which actually gives us a way how to have the commitment, or how to have a common key between these two, how to agree upon a common key, even if you have some conversation through some insecure channel. Okay, so you can understand that this boy and this girl will communicate with each other through some insecure channel, but still they will be able to at the end of some conversation they will able to establish a common key which will not be known to this boy. Okay, so if you think it in a deeply, then the question is, how is it possible? Is it really possible to do so? So this boy will send some message, and this boy will able to get this. This girl will send some message, this boy will able to listen it. Then at the end, how come they will be able to have a common key, but this common key will not be known to this bad guy? So it was a really a very difficult to at a very initial stage to understand, or to at least believe that okay, that can also be possible, like it can be possible if this kind of scenario may happen. But believe me, they came up with a nice way, and they first gave the idea of public crypto system, but actually they failed to do so in giving this a concrete example of a public key crypto system. But they came up with a scheme which actually given establish a common key between this sender as well as a receiver. So I will study this Diffie-Hellman key agreement protocol in details, maybe after 2 or 3 classes. But before that, first let us go to just 1 year after that incident, that means 1977, when another three very brilliant scientists, out of which two of them they are from computer science background, one from mathematics, they came up with an idea in 1977. So it was Diffie-Hellman was 1976, and this scheme was known as RSA, public crypto system, and that was done by Rivest, Shamir, and Edelman. Okay, so he is Shamir, he is Rivest, and he is Edelman. So they together they came up with a scheme, and they, if you Google it, you will find plenty of histories behind this invention. Okay, so you'll be surprised to know that all of them they tried to formulate a kind of function. That means that should be one way. What do you mean by one way? You can understand that it should be easy to compute, but it should be difficult to invert. That is known as one way function. And they were tried to convince or tried to make a scheme, but for many times they tried to do so, but all the times someone among these three tries to find some of the weakness, and they always succeed in getting some weaknesses. But ultimately in 1977 they came up with a scheme, and which is known as RSA public crypto system. Now you can understand that it's even the birth of mine, 1977. So before that, they actually invented that scheme, and that scheme is till now very much popular. Okay, so let us try to have a look at how this is happening and what is the basic motivation behind this. So the basic idea is that whatever he is going to send or whatever she is going to send, this bad guy will be able to understand, but still they are not be able to compute what is being sent actually. Okay, so that's the basic idea of RSA public key crypto system. So let us have a look at that. But before that, if you just have a look at this Wikipedia, so you'll find that when it was actually invented, and before that, so there is a kind of interesting news or interesting fact is that it was in 1977, but the British intelligence they claim that it was even invented by one of their employees known as Clifford Crocs, who actually invented almost the same thing in 1973. But since that guy was actually had a job in intelligence bureau of UK, that's why the scheme was not public, and it was made public after the date of this person, and it was declared 1997. So it was a kind of understood that RSA was the first scheme, but British intelligence they later on claimed that it was not the first, but they did it. But anyway, till now, this it is known as RSA public key crypto system, and it has been It has been a tremendous applications in various ways till today. Okay. So let us again try to understand how this concepts of public key crypto system came into picture. Okay, it would be a kind of motivation for public key crypto system. Now suppose again consider the same scenario, the sender wants to send some message to the girl, and if I ask you this question, very simple question, if the boy wants to send some message to this girl, then who should take the initiative first? The question is, who should take the initiative first? A very simple, very quick answer could be certainly the boy, but if you try to analyze the situation in a deeper way, then you will certainly understand that it should not be the boy, but it should be the girl, that who should take the initiative first. The question is why. Okay, now if I ask you the question, suppose this boy wants to send the message through say WhatsApp to this girl, and unfortunately the girl does not have any mobile, or maybe she has a mobile but she doesn't have WhatsApp installed at her mobile, then what will happen? Then suddenly, even if this boy sends some message to this girl, the message will certainly not be received by this girl. That means before sending the message, the girl should have some infrastructure present at his mobile. That means it should be the receiver end who start the initiative. Okay. So the idea is the girl should have some working mobile with a valid connection. Now then the next step would be the boy should collect her mobile number which is working to send the message, and then after getting the mobile number of this girl, the boy is going to send the message to this girl. So that's the idea. So in case of public key crypto system also, there we have a similar idea here also, like the sender and the receiver. In case of a sender and the receiver, it should be the initiative for the receiver to have the infrastructure first. That means if the boy wants to send some message to this girl in public crypto system, then it should be the initiative by the girl who should take first. How? The girl should make an infrastructure. That means she should have two different keys. One key she will keep with her, that is known as private key. Another key she will make it public. For example, the girl might have two different keys. For naive similarity, you can think of, suppose the girl has an email ID. The email ID is the public key. That means the email ID should be known to all, whereas the key, that means the password to enter into the email ID is kept secret to the girl. Okay, that means suppose this girl makes the public key public, that means that should be known to all. Suppose she put the email ID or her mobile into her website or somewhere, and then it would be the boy's duty to get the mobile or the email ID of that girl. So after getting the email ID, he is going to send the message. Okay, now when this girl will receive the message, as she has her own private key, that means the password to enter into the email ID, she can read, and nobody else should get the message because this guy does not have the password of this girl for entering into the email account. Okay, so that's a kind of very naive idea of public key crypto system. That means the initiatives should be taken by the person uh, to whom somebody wants to send the message. That means this is called the infrastructure. The infrastructure must be made by this girl having two different keys. One key she is going to make public, another key she is keeping with her secretly. That is known as secret key. By using the public key, the boy will encrypt the message and send the encrypted message through this insecure channel to this girl. Now you can understand that this bad guy will certainly get the encrypted message, but the problem is, since the private key is kept with this girl only and not with this bad guy, this bad guy will not be able to decrypt the encrypted message, but when the message will be received by this girl, by using the private key of that girl, the girl will be able to decrypt the message. So that's the basic idea of the public key crypto system. Okay. So as I just now mentioned, Rivesh Shamir Edelman, the scheme is known as RSA public key crypto system. So as usual, the boy wants to send some message, but as I just now mentioned, it should be the step one should be done by this girl. That means she should made some infrastructure. So let us try to put it here. So suppose here is the say recipient, so receiver, and here is the sender. Okay. So as I just now mentioned, the first step will be taken by the receiver, not the sender, by having some infrastructure. What the receiver will do, that means what the girl will do, the girl will first choose two large prime, choose two large primes. So what do we mean by large primes? I will come to it later on. Okay, say P and Q, prime say P and Q, and P should not be equal to Q. So practically speaking, they should be large enough. So usually for practical purposes, they should be around 1024 bits, means around 300 digits. Okay. So for practical purposes nowadays, these bits are also quite less. So now it's recommended to use around 2048 bits. So maybe around say 700 digits, 700 digits. Okay. So the question is, how do I get this prime? So in this course, we'll in details will describe about all those things. Then what the receiver will do, receiver will make product of these two and name it as n. So n is the product of these two distinct primes, p and q. Okay. Then she will calculate phi n. So what is phi n? Phi n, in my previous classes, I have already mentioned phi is a multiplicative function. So phi of pq, and this should be equal to phi p into phi q, because p and q are distinct primes. As a result, they must be relatively prime, and that becomes, what is phi p? Do you remember what is phi
P
p?
minus 1.
Very good. It should be p minus 1 and it should be q minus 1. Okay. Note that this guy, this receiver, knows p and q. Okay. So she will just calculate p minus 1 and q minus 1 separately and then just multiply them. And as p and q are distinct prime, she knows this product value will certainly be equal to phi of n. So she doesn't require to factorize it because she knows p and q separately. So she will just make p minus 1 and q minus 1 and make a product. Whatever will be the outcome will be same as phi of n. Okay. Until this, no problem. Okay. Then he will choose two interesting functions, e and q. Okay. So then chooses e such that GCD of e and phi n equal to 1. So she chooses a random e. So this e has to be a random e such that GCD of e and phi n equal to 1. That means e and phi n are relatively prime. So she is going to choose some e, of course within this range, some e, positive integer e, such that e and phi n is equal to 1. And if this is relatively prime, then you can understand that the multiplicative inverse of e exists. Then finds d such that ed is congruent to 1 mod phi n. This one, e mod phi n. So just now if you remember in my last classes, I talked all about this. So this is basically I am considering. So initially I was in Zn, and then so Zn was a additive group, and from Zn I talked about Un or Zn star, and then that was is a multiplicative group, right? So what was the order of this Zn star or Un? What is the order of Un? Remember, what is the order of Un?
Phi of n.
Very good. It was phi of n. So now I am considering basically Zn star, and they are the elements of this. Now when E and phi n, they are relatively prime, then if you remember, all the inverse exist. So which elements are there within this Zn or Un star? Sorry, Un or Zn star? All such elements which are relatively prime to n. As a result, their multiplicative inverse exist. So if you are somehow able to find some E which is relatively prime to phi n, then suddenly their multiplicative inverse will exist, and you will find 2. Then C finds D such that ED is congruent to 1 mod n. Okay. So how these steps could be done, now you can understand that we are going to do it with very large prime. We are going to do it with very large prime, around say 700 digits or 900 digits long primes. And so we need to do it very efficiently, otherwise it will take a lot of time. So how to find the GCD, how to find the multiplicative inverse of some elements, so they will be discussed in details in this course. Okay, so one of the very interesting topics that will be discussed here will be how this could be done in a polynomial time. So I hope you understand what do you mean by polynomial time. So naively speaking, they should be done in a very efficient way, because we are dealing with not a very small number, we are dealing with 700 digit long. I will show you how to some examples of this big long prime numbers. So these steps could be done very easily, and believe me, they can be done very easily by using your even simple small laptop or simple small computers. Now all the basics she had made, so now she is going to add two different keys. She is going to make E and N public. That means she is going to make it in a cloud, or maybe in a some server, or maybe in some her web page, or maybe within the Facebook, Twitter, wherever she likes. She will put these values, the value of E and N public, so they are public, and this value of D secret. So in fact this P and Q are also kept secret, so they are not made public. So mostly D will be required, but not P and Q. So you can understand that this is the secret key and they are the public keys. Okay. So if you just go to the steps, then the steps are very easy. Choose two large primes P and Q. For practical purposes, they should be of the same size and they must be distinct. Then she will calculate phi of n. So how to calculate phi of n? As she knows the values of P and Q, she is just making P into P minus 1 into Q minus 1, and that will in turn give her the value of phi of n. Okay. Now she will randomly choose some E such that GCD of E and phi n is 1. So we will show that how this GCD could be done, and that would be done by very simple, well-known algorithm known as Euclid algorithm. And you will be surprised to know that Euclid algorithm is very fast, very efficient, and it could be very difficult to get much better algorithm than Euclid algorithm for giving back you the GCD of two positive integers. Okay. Then what she is going to do, once she will get this E, then this GCD of E and phi n is 1, and that will in turn, as I just now mentioned in my last class, I have already discussed about this group. If you forget about it, please go to my last class, last video, where I have already explained about those things. So find the inverse of E, which we denote it by D, such that this is modulo phi n. That means ED is congruent to 1 mod phi n. That means E is the multiplicative inverse of D. Okay. So the question is, how can I find that big inverse of a very big number? And that can be done efficiently by using extended Euclid algorithm. Extended Euclid algorithm. So in my last class, I have also discussed about extended Euclid algorithm. If you don't remember at this point of time, please have a look at my last video where I have given you with some exercise how this can be done. Okay. So this is ED is congruent to 1 mod phi n. Then what we had basically all the elements that will be required are done. N and E will be kept as public values, whereas the D value will be kept with her secretly. Okay, so that's the infrastructure made by the girl. Now it should be the sender's responsibility what to do. First thing that sender is going to do is collect the public key of the sender, I mean of the receiver, of the girl. Okay, of the receiver. That means that is N and E. N and E. Okay. Now she knows the public key N and E. Second thing is that he wants to send some message. So convert the plain text M in such a way that 0 less than equal to M, strictly less than N. That means suppose he wants to send some message in English, then by some means convert the plain text M into some number so that the number should lie between 0 and N. It could be done in very different ways. For example, one very simple way could be, so we know that all the characters has some ASCII value, say A, B, C. There are many like A, B, C. There are some special symbols like star, something. So all of them, they does have a kind of ASCII value. So it's nothing but a kind of one-to-one correspondence between this alphabets with some values between 0 to 255. That means there are altogether 256 characters which can be encoded by using this ASCII value. This ASCII value. So can you tell me what is the ASCII value of capital A? Anybody? What is the ASCII value of capital A?
65.
65. And what is the ASCII value of small a?
97.
97. Very good. So one way you can convert like a as 65, small a as 97, and so on. So that, see, you can understand that now there is no more a. So this is just an integer 65, and you can think this 65 as your plain text M. Or if they are too big, that means P and Q are too big, then you can understand that converting a into 65 may not be a very good idea. In that case, you can convert maybe consecutive 8 characters. That means each character is 1 byte long, so you can encode 8 characters altogether. Okay, that means 64 bits altogether, and then convert the 64 bits into the corresponding integers. Suppose M is that integer, then consider M as that integer and consider M to be your plain text. Okay, so there could be plenty of such ways to convert a message into a number, and that method has to be public. That means that method should be known to all. That means this girl may also specify that issue, that okay, how to convert your plain text into ciphertext, and sorry, a plain text into a number, and so on. That means that is known to both of them. Now what he is going to do, the final step is he has m as the plain text. Now he wants to convert the plain text into ciphertext. So if C is the ciphertext, then that is nothing but m to the power e modulo n. Look at that, this e and n, these two values, this e and n, these two values are public. So this boy knows knows these values of E and N, and M is the message, the plain text message. So certainly he knows this. So all the information he requires, he has already with him, and he computes M to the power E modulo N and sends this C as ciphertext to the girl. Okay. Now the receiver will again act. So what will be the process? So first will be collect C from, say, sender S. Then this is a very simple step. Then she will compute simply C to the power D modulo N, and miraculously that is equal to M modulo N. Okay. So that part you need to prove, that how this is done, or why C to the power D modulo N is actually equal to M. So this is your homework. In my next class, so in my next class, I will talk with this, with the mathematical details, why this is so and how this is happening. Okay. So it's very easy. You use the in my last class, I talked about Euler's theorem, Fermat's little theorem, and that will be used to prove this result. Okay. So till now, any question? If you have, please don't hesitate. So I'm repeating once again. Step one, that should be the step by recipient. She will choose two large prime P and Q. They has to be distinct. For practical purposes, they have to be of same size. Then she will compute n, which is nothing but the product of pq, and they are going to calculate p minus 1 into q minus 1, which will in turn will find the value of phi n. Then chooses e, a positive integer, such that gcd of e and phi n equal to 1. Compute d such that ed is congruent to 1 mod n. So this algorithm will be done by Euclid algorithm, and this algorithm will be done by extended Euclid algorithm. Then she is going to publish this value of n and e as public key and keep with her. This d value will be required, but p and q values are also kept private. That means they will not be used, but later on we will show that if p and q are known to anybody, then she or he will certainly get this value of d. That's why this p and q will be kept secret. Then it will be the turn for the sender. The sender will first collect this public key, as just now I have shown. Then she chooses m, the plain text value, in such a way that will be within this range 0 to n minus 1. It could be less than equal to even, and then computes m to the power e modulo n, m to the power e modulo n, and that will be the ciphertext, and send this ciphertext to Bob. Okay, I mean to the girl. And now it will be the turn for the girl. The girl will compute c to the power d, c to the power d, c to the power d modulo n, and that will in turn give her the value of m back. So this is my first homework, that you need to find how this is happening, and as a simple exercise I can give it to you, and I can give you a hints like Fermat's little theorem and Euler's theorem will be useful, that I taught you in my last class. Okay, so you will find this very difficult to understand. Okay. So next, we'll show that how why this is happening and how depends on a problem hardness assumption that now we are going to show you what is the hardness assumption. For mathematician, it's really difficult to appreciate this problem because the problem is the factorization problem. What it says? So it says that if I give you say some positive integer, give me the factors of it. For example, if I give you 35, then the point is you need to give me the two prime factors of it, like 5 and 7. That's the factorization problem. So if I ask you to do so, like if I give you this number and if I ask you to factor this, you will certainly give me this very quickly. If I give you this number, it may take some time, but you will certainly say that, okay, I'm not going to do it by hand, but instead I will make a programming and that program will give you this result. But if I ask you to factor this number, then you will be little stuck, right? It's a quite big number and I give you to factor this. But you will be surprised to know that this number is nothing but the product of these two big primes. So here maybe I'm not sure how many digits are there, say maybe 300 digits long maybe. So this 300 digit P and Q, if you make a product of these two, you will get this number. Okay. But if I give you this number and if I ask you to solve this, to give me back this P and Q, you will be stuck. And not only you will only be stuck, if you do it by your computer, your small computer will also be stuck. So you may think of, okay, my hard disk or your specification of your mobile or maybe of your laptop or your desktop is not that good, so why not try with your supercomputers? And you'll also be surprised to know that it will not be possible for a supercomputer even to factor this very quickly. It may take around maybe 50 years to solve this problem, because till now there is no algorithm known which is polynomial time in nature and which can factor such a big number in polynomial time. It's not yet publicly known. As a result, not only you with your small laptop or computer, it will also be difficult for a supercomputer even to factor this big number. Whereas, if you heard about the quantum computation, so in quantum computation, that factorization can be done because in quantum computation, there is one algorithm known as Schnorr's algorithm, which is capable of factorizing this big number in polynomial time. That's most important. In polynomial time, there it is possible to factor. But the problem till today is that we do not have a quantum machine yet that is capable of factorizing things. So in future, if one day somebody will be having a quantum machine, then you can apply that algorithm to factor this in a polynomial time. But till now, we do not have that infrastructure. As a result, this problem is considered to be a computationally hard problem. Okay, and based on this computationally hard problem, the RSA crypto system is mostly based on. Okay, so the question is why and how. So have a look at this. So here, suppose she is the receiver and she is the sender. Okay, so it was the initial phase of the receiver. Then the first thing was done by receiver, then it was by sender, and then again by the receiver. Okay, so what are the information that the attackers, suppose the attackers is lying in between. So what are the information that the attacker knows? Say this is the attacker. What are the information that is known to that attacker? First of all, when the receiver makes her things public, that is the value of n and e that was made public, right? So she knows the value of N and E from receiver. Okay. Now, when sender sends C, which she knows, the attacker knows that is m to the power E modulo N. Okay. So this information is known to the attacker. The question is why this receiver is capable of getting the value of M from C. So she received C, and how come she able to know the value of M, whereas why this attacker is unable to get the from C the value of M? What stops him to getting this value of M from C, whereas the receiver, she is capable of computing the value of M from C? Any guess why it is happening so? Any guess why it is happening? Sorry, couldn't get you. Okay, uh, not properly getting your answer, but of course you may think of that. Okay, she has the D with her, right? The key which was secret, and the D was not present with the attacker. Now, first let us try to have a look at why the attacker doesn't have D. What is the difficulty of getting D? She knows N, she knows E, just she needs to calculate D, which is the multiplicative inverse of E in phi n. So what is the difficulty that he is facing but this girl is not? What is the difficulty that you think of?
Phi n.
Exactly. So he knows N, right? But he does not have the idea of what is P and Q. She does not, the attacker does not have the idea of P and Q, but he knows N. So the question is, if he can compute phi n, then from phi n he knows E. So just like this girl, how she calculated D, she could also be able to compute this value. The only difficulty that this attacker is facing is that he does not have the values of P or Q. As till now, just like factorization, there is no efficient polynomial time algorithm is available in calculating phi n if you are not able to factor n. So once you know the factorization of n, so you remember in my last class I have explained like this: if this one into pk alpha k, then the value of phi n was n into 1 minus 1 by p1 dot dot 1 minus 1 by pk. But here I assume that n can be represented as a product of primes. But if you do not know the prime factorization of n, then till now there is no efficient algorithm is known which can compute the value of phi n. As a result, from n, it is not very easy for the attacker to calculate phi n, and as he is not able to calculate the phi n, it is also difficult for him to calculate D from E and N. Remember, once he gets the value of P and Q, he can very easily compute phi n, and once he can compute phi n, he can very easily compute by extended Euclid algorithm the value of D, just like this girl. But as he does not have the factorization of P and Q, it is not very easy for the attacker to calculate the value of phi n. So in that way, you can think of very broadly or loosely speaking, RSA is based on this factorization algorithm. Okay. So is it clear to all of you, the algorithm and why the factorization is playing a role? So now you think of, suppose A and B, they want to calculate or they want to send some message here and there in presence of some adversary. Okay, in presence of some adversary. Now something, both of them, they must employ something such that if they know some of the information, they will able to calculate something, but if that information is not known to them, it will not be possible to calculate them. So it was a nice idea for Adi Shamir, Adelman and Rivest to came up with such a nice scheme, which was based on the factorization problem. The problem was it was computationally difficult to factor n if only n is known to you. Okay, so based on this algorithm, they came up with the nice RSA crypto system, which is still very much useful in day-to-day life. For example, when we talk about the SSL algorithm or SSH algorithm, they are very much used. When in case of a handshaking algorithm, they are used. So there are plenty of places for e-commerce, and many places you will find that RSA is still very much useful. Okay. Now, is it clear to all of you? Any question? Any question or queries? If you have, please let me know. Any question? Okay. So if not, then few things that I want to mention here is uh, end-to-end encryption. So I mean, you might have heard about this end-to-end encryption in everyday life, because in WhatsApp, every time you send some message, it says that it's end-to-end encrypted. So broadly speaking, it's not the exact scenario, but it's a broad aspect of it. But in this course, at the end of this course, you will certainly have some projects. And one of the projects could be to explain with details all the steps behind this end-to-end encryption by WhatsApp. So if you just Google it by searching the name as WhatsApp white page, WhatsApp white page for end-to-end encryption, you will get that Signal. There is a protocol they use called Signal. You will get in details of it, but at this point of time you may not know all the tools that are used there. But in our course we will learn about all the tools that are used in the Signal protocol, and at the end of this course you will certainly able to understand what is Signal protocol and how it works in detail. So that would be one of the projects, and that you have to give a presentation uh, in this course. Okay, so what is this end-to-end encryption then? So it actually uses the basic concepts of this public key crypto system. So as you understand that he is the sender, she is the receiver. So just now, as I mentioned, in case of public key, it should be the responsibility for the girl to start with. So when we install WhatsApp at our machine or at our mobile, then it at that time two keys are generated. So one is public key, one is private key. Now this the at the mobile of this girl, this private keys are kept, and the public key is being sent to the server of WhatsApp. Okay, so at the time of installation, two keys are being generated. One key she keeps with her mobile, another key is being sent to the server of WhatsApp. Now when this boy wants to send the message to this girl, the boy sends a request to the server to give the public key of that girl. Now the server will send the public key of the girl, and this boy will receive the public key. Based on that public key, the boy then encrypts the message and sends the message to the server, and then the server sends the message to this girl. Okay, now since the girl has the private key with her, which is kept at her mobile, the girl and only girl will be able to decrypt the message. Since it comes to the server, you may think of, that's why when you look at the WhatsApp chat box and WhatsApp information, there you find that the WhatsApp says that even for WhatsApp it is not possible to get the message. Okay, so that's the formally says. So that's the idea of end-to-end encryption, because it's encrypted from end to end. That's why this is known as end-to-end encryption. And is the idea clear to all of you how it works? Okay. So if it is clear, but then a certain question that may come to your mind, that if it is end-to-end encryption, then how come you sometimes you get the message of somebody who are targeted, right? Sometimes you get the message. So it's not officially given by that company, uh, that how they give the message, but if you Google it, you will find that there is a concept called backdoor method. Okay, so in backdoor method, according to internet, it says that there is a kind of mechanism through which, in case of WhatsApp even, they made a kind of mechanism in which they will be, I mean, even if the sender or the receiver, they will not be able to be notified that their message has been forwarded to somebody else. So what these companies, they claim that whenever you send a message, this message will be encrypted with an unique key, and some notification will be sent. You can check whether that keys has been used or not, but there is a concept called backdoor, through which even if that message can be sent to some third party, even if without the knowledge of both the sender and the receiver. So that is known as backdoor process, and you can Google it to know more about it. So I'm not going to give details. It's a kind of research work that many teams there now currently they are working on. You can Google it and you get all the information behind this. So this could be one of the projects that you have to make it, maybe from implementation viewpoint or from theoretical viewpoint, how this works. So you can divide your teams into several teams, so that one of the teams will get this project. So that I will discuss in details. So till now, any question or any comments? Okay. So I will show you now this how the big primes are being generated by using software called SageMath. Okay. So this is an example of a screen for the SageMath software. Many things can be done. So those who are, so this is, you can see that this is 1,000 digit. So it's a next prime of 2 to the per 1,000. So huge number that you can understand. So around 300 digits long, or it consists of 300 digits. So it's a very good software because you don't need to write many things. It can be automatically done. So this is factorial 10. So you may think of factorial 10 is quite less. Why should not have factorial 100? It gives you the result very easily, very quickly. Why not 1,000? This is the result for 1,000. I'm sure that you might not have seen. Those who are applying for ISI exam, for them, one of the questions could be how many zeros are there at the end if you calculate 1,000 factorial. So that you can very easily calculate mathematically, but you can also check by using this. Not only 1,000, you can make it 10,000 and something like that. So if you make it 10,000, then also it will give you the result, and it may not show you the result as a whole, but you can check it the full result in this file. Okay, so now you can understand that my small laptop is capable of calculating these things very efficiently, very easily. So suppose you want to calculate next prime, say 100 gives you 101. So if you want to calculate 1000, it gives you 1009. So you can see that it can be done very quickly. Maybe 1 lakh is something. I mean 10,000. Maybe if you put some any arbitrary number on it, and also it will give you very quickly the answers. Now you can understand that to deal with, if you write a C program which will give this big number, or which will take this big number as input for your primality testing, then writing that C programming, C code is not that easy. But here we are fortunate that we have this kind of programming packages are there which are free to use, which are open source software, unlike Mathematica or MATLAB, but it's free and very efficient. You can install at your desktop or laptop. Even you can work through your mobile, but understand that if you work through the cloud, then certainly that I mean this process will be quite slow. But it's good to have it at your own desktop or your laptop. Then it would be easy to work upon. Okay, so let us try to have a look at RSA crypto system by using this, but I will do it only for a single digit number. Say first I need to choose some P and Q. Say P is my, say, next prime of say 100. If you put it, if you just print P, gives you P, then Q could be, say, Q equal to next prime of say P itself. Then if you print P, print Q, then you can see that 101 and 110, so they are twin primes. Okay, now it's your N. So this is what I'm doing, is basically the uh, steps for setup stage. That means the initial step 1 that could be done by the receiver. So she calculates then P into Q. Okay, then what she needs to phi n, say phi equal to, what is this value, she knows the value of P and Q, so she is going to calculate this star Q minus 1. Okay, let's print phi. So you can see that 101, 102 are the P and Qs, and this is the value of phi of P into Q. That means P minus 1 into Q minus 1. Okay, now what they require? They require a E which is relatively prime to phi n. So if you remember, they require E which is relatively prime to phi n. So they require, choose a positive integer E such that GCD of E and phi n equal to 1. So let's start with some E, say maybe E equal to say 10. So usually it is recommended that E should be more than 2 to the power 16 for 2014 bit. So let's start with, so this is a toy example. So let's start with E equal to this, and I put a while loop, while GCD of, so here you don't need to write the program for GCD, it's already available. E and phi is not equal to 1, not equal to 1. So those who are comfortable with Python, they are capable of understanding how I am writing this and how the alignment is taking place here. So while GCD of this E equal to E plus 1. Okay. So let's print E. Print E. So you can see that it starts with 10 and suddenly it gets 11. So you can also do like you can randomly choose E. So you can also use a random integer function which will, instead of E plus 1, it's actually it should be a random integer. So you can ask for a random integer between some value E and phi. Sorry, this 10 and phi. In between, it will choose some random integer E and phi, and then it will give you this value. So maybe a random integer. Uh, so it's very easy for you to search in Google. So how to use random, how to get random integer, how to get random integers in SageMath. Okay, if you type this, so this is rand int 02. Okay, so this includes or random number between something. So if you say equal to rand int 10 and 5, so you can see that now it is taking some E which is random, and it is not like at first chance it gets this value. So start with 10, it checks whether 10 and phi, this value is phi, is 1 or not. So we can see that 10 value is not 1, so it gets into the loop and it prints like rand int between 10 and phi. So first time, suppose something, let's see how many steps it get. So I print E. You can see that it tried with many steps, and after some step it get this value, and that it has given you as a integer E, which is relatively prime to phi n. Okay, so I think it's clear to all of you now. So E equal to rand int 10 phi. So 10 comma phi is an, you can check how this function works in SageMath. So it brings a, it at every time it calls, it actually gives you a random integer between 10 and phi I, and then it checks whether that is not equal to 1 or not. If it is equal to 1, it comes out of the loop and print E. So whatever E will get, it suddenly your relatively prime with phi. Now what you need basically a D, compute D such that GCD E and D is 1. So now what I'm going to do is, so print, maybe I can put it in this way, so that will be useful for my, okay, let's, I will put it drawn. So D equal to, now you can do it very easily by using this function. So this mod function, capital M, that too with capital MOD, it gives you the value of, I want, how much I want ED congruent to 1 mod phi n. So that means you are going to divide it by this, and I want to calculate the inverse of E. How it is calculated? E comma phi to the power of -1. So what does it mean? Let's check. It like, so I want to calculate. So what is my D? D is my E inverse modulo phi n, right? That means ED is congruent to 1 mod phi n, and this mod function is represented by this. So a n to the power b, it means a to the power b modulo n. Okay, so now if you consider n to be my phi n, so this is my b, b is now my -1, and a is my e. So e to the power -1 modulo phi means modulo phi n. Okay, so print B. You can see that if you make a product and divide it with by phi n, you will get 1. So let's see, just as a check. So E star D, and if you take a remainder with phi, it should give you 1. You can check, it gives you the value 1. So it's just a check. Okay, so now you are having all the values of E, phi and all, so you can write it, print the public values are, which are the public values? Can anybody tell me? What are the public values? Anybody?
N and E.
Very good. N, comma E. Let's see how it works. Yeah. So n was my, I printed n. No, I never printed n. So print n. So that was my n, 10403, and it was my, so 10403. Note that every time I run, it will be changed. Now I have used random int. See, so now the value of E is this. So let's put it here, E equal to this. So D equal to this. Now you see that every time E and D will be changed. So now it's 7441, and if I run it, now it's 1723, because all the time I am changing it because it's calling the random function. Okay, so this was my n value and this is my E value. Okay, and then the private value, print the private value. I'm just putting D only. Okay, B. So you can see.
So T is missing.
Sorry. Oh, print. Yeah. Thank you. That's why it has given. So it's a, like Python is the interpreter. That's why it gave the, till now, till this, it has given you the correct answer. But here it was unable to find pin where T was missing. That's why. But now it will be fine. Okay. The private value is this. So you can see that all the time if I run it, it will change. Okay. Okay. Now next time, what I'm going to do is I want to I want to encode it, right? So that will be the idea of sender, not the receiver. So what he will do, he will collect the plain text. He will collect the values of E and D. Remember, I need to put this values at N and D. So what is my N? N is my 10403, right? And my E is 5923. Well, now he has some plain text, suppose m value. So can you tell me some m value which is less than n? Here n value is this. Anybody tell me some message in numbers within this range, 10403. Any number, anybody? Any number?
10,000.
10,000. Okay. Good. 10,000 is within this range. Very good. Now what he is going to do? He is going to make C. What is my C? C was can now tell me by using this mod function. What is my C? C is m to the power e modulo n. Now using this mod function, can you tell me by using what should I write here? What should I write?
mod n comma n to the power e.
Mod m comma n to the power e. Very good. That's what I write here. Mod m comma n to the power e. Yeah, to the power e. And then print. So this is now my ciphertext. Okay. Now it's a time for decryption. So what the decryption will do? He will collect this C equal to 7374, and then what she is going to do? M equal to, say if I put capital M equal to, what should I write? Tell me. What should I write? So it was the decryption algorithm. What should I write then?
So C to the power D.
Very good. In terms of mod,
Mod of comma to the power
to the power D,
D.
and print M. See, 10,000 is back. Clear? So it's very easy. And when you are able to understand how this mathematical portions is being done, you will appreciate how it's working. And it's also very easy to implement in Sage, but now it will be an implementation issues for you. So as an homework, I will prefer you to do it either on Sage or on any language that you are comfortable with. So in my next class, I will ask you to show me the implementation of this RSA crypto system, firstly with one single number, and then for more practical uses you can understand that it has to be with a text. That means I will give you a text, so you will encrypt that text, you will give me this value, I will return you back, or maybe the other way around, it could be a test, I will give you the public and public values, and you will collect my public value, you send me the encrypted value, and I will tell you what was the plain text. So that could be a nice way of seeing the whole thing. Okay. So any question till now? Okay. So
Can you please say the decryption part once?
okay, sure. Decryption path in Sage or in, you want to see it
Sir,
in
in
Sage?
Sage.
Okay. Yeah. It's done. So if you want to make a screenshot of it, you can also. So this is the, I can reduce it a bit. Then this is your encryption. So this is not encryption. This is your initial part. Then this is your encryption, this part, and this is your decryption, this part. So if you want to take a screenshot of it, you can also take it. So a simple thing that I have used, nothing else. So all the things are already incorporated. So if you want to implement it in C, then you can understand that what are the functions that you need to implement. that are not very difficult, but the point would be if you deal with bigger numbers, then what will happen? Okay, now you can understand that it can deal with very big numbers. For example, suppose it's your, let's check once again. If you say your prime is maybe this little, little with this, and let's do it once again. Yeah, nothing L came. But if you, so this is not a square and multiply method, but if you do it with square and multiply method, then you will able to see that this even can be done in a nicer way, and that will give you the exact answer. So in this course we'll also learn how to have the square and multiply. All the mathematical tools that are being used here will be explained in details, and as well as the implementation issues. So you'll have to implement all of them by using any of such programming languages. So now it's my n is my this, n is my this, so this is my n, this is my n, this is my e, and m, let's see, m is kept as usual, so that is my c. Now put this c as my here, and let's see if it's back. Okay, again it's back. So the question is, how do I do it in a more efficient way? So three important functions are important here. One is GCD algorithm, which will be done by Euclid algorithm, then finding the inverse, and that will be extended Euclid algorithm. And third one is the a to the power b modulo n, and that will be done by square and multiply method. Square and multiply method, and they all of them are polynomial time, and they are very efficient to do. That's why the small computer can also do this. So in this course we'll talk about all those things in details. So till now I am following the book Basic Modern Algebra with Applications at chapter 10. So there you will find all those things. So all of you are requested to have a look at this. In my next class, I will discuss more about it and more attacks on RSA, how very interesting attacks that is known as bidding attack. I will explain with great details how that can be done, and also with some implementation way that I will show you how this scheme could be attacked efficiently. Okay, so till now, that's what I want to say. If you have any questions, please let me know.